So problem number 4 is the first one we're going to look at, which says the following. Okay, you have the K equals 2.6 times 10 to the 8th at a particular temperature. 2.6 times 10 to the 8th. Whoop, 10 to the 8th. 10 to the 8th. At a particular temperature. Okay, the temperature doesn't change, so that is not necessary, but it doesn't change. The equation is 2H2 plus S2 at equilibrium to make 2H2S, and they're all gases, which means this is a homogeneous equilibrium. They're all gases, which means we write our K expression. It's products, which is H2S squared, over reactants, which is H2 squared, and S2, no squared. So this is our equilibrium expression. It says the concentration of H2 right here is 0.002 molar, and that S2 is 0.0010 molar. That goes in there. It says what is the equilibrium constant of this, given the K, 2.6 times 10 to the 8th. What is the concentration of the H2S? So in the problem, we know 2.6 times 10 to the 8th equals x squared, which is our unknown, divided by 0.0020 molar squared times 0.0010 molar. So this is our equation to solve for x. So we take 0.0020 squared times the 0.0010 molar times the 2.6 times 10 to the 8th equals x squared. And then we have to take the square root of both sides to get rid of the x squared to get our value for the concentration. So for this one, 0.0020 squared times 0.0010 times 2.6 EE8, and it's a positive 8. Yep. And this gives you an x value of 1.04. I got 1.04, interesting. And that should be the concentration of x. Okay. So 1.04 is not one of the options, but 1.02 looks like it's the closest. What did we miss? Oh, the square root, yes, of course. There you go. So x squared, you square root it and it equals 1.0198, which is equal to 1.02. So that is how to do that. The step most people forget is the equilibrium expression. They forget to square the H2S and square the H2S, okay? Most people remember to do the square root, except if you're Mr. Christopher. All right, next one. Number 5, let's look at number 5. If it's similar, I'll tell you as such. Calculate the value of Kc. So it's similar in the way you set it up. Equilibrium, then plug in the values. Anything we're missing? So the one thing it's missing there is the PCl3. For that one, you can assume, I believe, the concentration of the Cl2 is equal to the PCl3 because it's a 1-to-1 ratio. So that's the only weird thing on that one, is it doesn't tell you the PCl3. I'm sorry, initial concentrations, pardon me. So on number 5, it's a little trickier because it's not all at equilibrium. PCl5 breaks up into PCl3 plus Cl2. It says the initial concentration of the PCl5 is 2 molar. the equilibrium concentration of the Cl2 is 0.3 molar. So this is a way of counting for the initial, the change, and the equilibrium. It spells out the word ice. It's a computer. It's not good. So to get, you start out with 0 of this and 0 of this initially. You want to get 0.30, so you have to add 0.30 to this. And you also have to add 0.30 to that. So the equilibrium concentration would be 0.30 of this. In order to get 0.30 from that side, you have to subtract it from this one, so that's 1.7 molar. So these are our equilibrium concentrations. Once we have our equilibrium concentration, we can then plug it into our equilibrium expression, PCl5, and they're all to the first power, so our Cl2 is 0.3, our PCl3 is 0.3, and our PCl5 is 1.7. So 0.3 times 0.3 divided by 1.7 should give us the value of K for this particular problem of 0.05294. And that should be one of the options for number 5. Number 11 is the next one. Yes? Okay, so in this equation, we're starting out with all of this and 0 of those. So any of these that are made, it told us that this much Cl was made, so it has to come from the other side of the equation. So it has to come from the reactants. So if you get 0.3 moles of Cl2, the ratio is one of these is proportional to one of these. So if you need to add 0.3 from here, you have to subtract it from the reactants. Does that make sense? Kind of. The reason it's 0.3 lost here makes 0.3 and 0.3 here is PCl5 is composed of PCl3 and 2 Cls. This formula, these are equal to each other. When PCl5 breaks apart, it breaks up into 2 pieces. Piece 1 and piece 2. If you have one PCl5, like one of these, it breaks up into boop, Cl2 and PCl3. So it's a 1 to 1 to 1 mole ratio. That makes sense? So that's involving the stoichiometric ratio. If we look at number 11 as an example, who had number 11? Okay, number 11. All right, number 11 is asking what is the KSP for silver bromide if the molar solubility is 8.8 times 10 to the negative 7th moles per liter. Now, this problem doesn't give you a lot of information, but it says it's a KSP problem. And a KSP problem is always when you have a solid dissolving at equilibrium with its ions. So this is a special equilibrium. In this equilibrium, now we just write our K expression. K equals our silver times our bromide because they're aqueous. But do we include the silver bromide solid? Nope, we don't include the silver bromide, so that is our KSP setup. Now, once we have our KSP setup, we look at the problem. The information we're given is moles per liter, which is equal to molarity. Molarity is in concentration units. So we're given the concentration in this problem. Now, if the concentration of this was S, the concentration of this would also be S. So these two are always going to equal the concentration value because it's a 1-to-1 ratio. So the concentration of the silver is equal to 8.8 times 10 to the negative 7th molarity. And the concentration of the bromine is exactly the same in this case because it's a solid dissociating into those ions. So you multiply these two together and that will give you your KSP value. Does that make more sense, Amanda? This is what we just talked about earlier today. So if you couldn't do that before, that's a special K problem. KSP also stands for special K, solubility product. 12 and 13 are also KSP problems. No, 12 is, I'm sorry. So the problem with 12, it's a little bit trickier, but I will show you this. However, I want to give the warning. You will not have to do this on the test. You will not have to do this on the test. That's the warning. So if you don't want to watch, that's totally fine. I understand. Number 12, you will not have to do on the test. And this is what we just learned today. Now, number 12 is a little tricky because the formula is different. HgI2 breaks up into Hg and I2. What would be the K expression for this one? If this is solid and these are both aqueous, K equals what? So we do need to be able to do this for the test. This part of the problem. You're given an equation. What's the equilibrium expression for that equation? What is written first? Hg plus 2 times what? I. And what power is the I to? Squared. Now, this here would be how to do the equilibrium. If you were told the concentrations of this or the concentration of this, you could do the problem. Okay. Now, in this particular problem, it does give you the solubility. So it gives you the S. The problem is, if this is S, this one has what ratio? What's the ratio between the H, G, and the I? 1 to 2. So if this one is S, what's this one have to be? 2S. So then you just plug in the value for S, which is 2.2 times 10 to the negative 10th. That's for this one. And then you do 2 times the 2.2 times 10 to the negative 10th. Squared. It must still be squared, and that will equal your KSP value. It's a little more challenging if you had to do this backwards, but it would still be the same setup. The same setup, you would just have to solve your equation differently. Does that make some sense, Amanda? That was given in the problem. It was the moles per liter, which I know is molarity. In the problem I did, that was where I got it from. It might not be the same on yours. And you use that value in here. It has OH parentheses 2. Yeah, the OH ion would be the one that has double the moles. Yeah. Is your problem with calcium hydroxide or? Yeah. So it's a similar setup. It'll be a similar ratio. It'll just have different numbers and same 1 to 2 ratio. Yeah.
On the bottom, is that 2 times 2 times 2 times 10 to the negative 10?
2 times 2.2. It's double 2.2 times 10 to the negative 10. Yeah, sorry about that. It does look all the same to me. Your version's different? Yep. So whatever your version says, you do the steps based on the reaction you have. I think that would work for nickel hydroxide. We'll draw out the equation for it. It should be similar. All right, the next questions we have are on fire. Not literally. On fire section for period 2, let's look at question 40. See if I can get to question 40 here. Is that the one with the sodium hydroxide being dissolved in a solution? All right, so if I can call this up, I will see it. So on question 40, you have a certain amount of sodium hydroxide, and it's dissolved in a certain amount of water. So let's view someone's quest to see number 40. All right, number 40 is asking for the temperature change. So it wants the delta T when 24.6 grams of sodium hydroxide with a negative 44.5 kilojoules per mole enthalpy of solution. So this is the delta H when it is dissolved in a solution. It's dissolved in 160 grams of water. And it says that the specific heat capacity of the solution is equal to 4.18 joules per grams Kelvin. Now, the good thing about Kelvin and Celsius is even though they have a different scale, 1 Kelvin is equal to 1 degree Celsius. So you can change this to a degree Celsius unit here, first of all. The next thing is you've got 24.6 grams of NaOH. So you have to convert the grams to moles of NaOH. In NaOH, the molar mass is 40 grams per 1 mole. So you cross multiply this, 24.6 divided by 40. This gives us 0.615 moles of NaOH. Then you use the heat for dissolving this to find the kilojoules produced. So if you had 1 mole, it would produce 44.5 kilojoules. 0.615 times 44.5, and this equals 27.3675 kilojoules. Now, this is the amount of heat that is given off by the solution, given off by the solid. So that means it's being absorbed by the solution. So positive 27.3675. If you multiply this by 1,000, 1, 2, 3 places over, this gives you the amount of joules that are going into the solution. Once you have the joules that go into solution, you can use your mass times specific heat capacity times change in temperature. The tricky thing about the mass is this is 24.6, this is 160, so you have to add them together because it's for the solution. So 184.6 grams is for the entire solution. This is 4.18 joules per gram degree Celsius, and the delta T is what you don't know. So then you just solve for the delta T, divide by 184.6, divide by 4.184, and this gives you 35.4672 degrees Celsius. So that is how to go about a problem like that. Yes, sir?
So will we be given any constants or like specific heat and stuff like that? Or
You'll be given any constants you need, yes.
Okay.
Only thing you won't be given is specific heat capacity of water is 1, and in joules it's 4.18 joules per gram degree Celsius. So that's the only conversion factor you would need, as long as you know water is 1. Yeah. Whenever it says enthalpy, that is equivalent to heat of. So it says enthalpy of fusion, that means it's heat of fusion. Enthalpy is just for a particular temperature and pressure. Heat of reaction is only when it's at 25 degrees Celsius and 1 atmosphere. So if you have enthalpy, it doesn't say anything about the temperature or pressure, just means solve for this condition. So it's just another word that chemists use for heat of reaction or heat of vaporization or heat of fusion for a particular condition. Because it does change. If you're at a different temperature, the heat changes, the energies change. The formula. Alright, so formulas. For all the heat of reactions, these are the formulas we have. Delta H, which means heat of. For the heat of fusion, you multiply that by the mass, and that tells you the enthalpy change. If you want the enthalpy change in a reaction, what you do is you find the heat of formation of the reactants, okay, and you add to this the heat of formation of the products. But heat of formation means that the element is forming a compound. This has only happened when you form products. When reactants, they don't form products, they do the opposite. They're breaking apart. So you take the sum of all of these, and you subtract all of these, so you add them all up and you give it a negative sign, then you add it to the sum of the products. That's one way to get the enthalpy or the heat of a reaction. The other way to get a heat of a reaction is if you're given the energy of breaking bonds. So the energy of breaking bonds minus the energy of making bonds. Breaking bonds is dealing with the reactants, making bonds is dealing with the products, and that will give you the delta H as well. For vaporization, it's a similar equation up here. Delta H is delta H of vaporization times the mass. And the last thing that can sometimes be used is if the delta H of vaporization is in kilojoules per mole, you need to have this in moles for it to cancel out. So those are all of the possible options around delta H. Which part of it? Any of it? I'm sure it is fair game. Any of it could be. We focused on the breaking and making of bonds, but the heat of fusion and heat of vaporization, that was with phase change. 2 and 44 are similar. All right, on question 43, we'll look at this first because this deals with the molar heat of fusion. For water, this is 6.009 kilojoules per mole. And it says how much energy would be required to melt 10.76 moles of ice. So 10.76 moles, you want to know how much energy. So this is the easiest way to do a problem like this. You set up a proportion. Does that make sense? So I don't memorize the formulas, I just look for the proportion and convert it. In this case, it's already in moles, so 6.009 times 10.76. And this gives us an X equal to 64.65684 kilojoules. So this is a delta H problem that you were asking about a minute ago. That's an example of one that you should be able to do. For problem number 42. For number 42, it's asking you to find the energy for changing water from negative 18 degrees. And it goes up into water at 64 degrees. So in order for this to happen, it has to go through a phase change at 0. So our heating curve would look something like this. there are 3 different steps. Here's it as a solid, here's it as a liquid, here it's going from a solid to a liquid. Step 1, step 2, and step 3 need to be done separately. So step 1, to do that, we have a change in temperature, so we use our Q equation. Step 2, we have a change in phase, so we use our delta H equation. This happens to be the heat of fusion times the mass. And for step 3, it's a change in temperature as well. So the mass of the sample is always the same because it doesn't change through physical changes. The mass is 44 grams. In this particular one, you plug that in here. You find the specific heat capacity for the solid and for the liquid here. And then the change in temperature, this one it goes from 18 to 0. So that's 18. From this one it goes from 0 to 64, that's 64. The delta H of fusion is given in the problem as 2260 joules per gram. So you multiply these out, you get joules for each of them. Then you add all of them together and that gives you the joules total. If you divide it by 1,000, that will give you your answer in kilojoules. So that's how to go through a problem like 42 or 44 on the Quest. Yep. Computers are over in this room over here.